So first of all, I would like to join all the other speakers in thanking the organizers for organizing this very interesting conference and inviting us to this lovely place to meet together. And as you heard, I'm going to talk about, I'm going to be the first to talk actually about two-dimensional topological insulators rather than quantum Hall or spin liquids, and in particular on what a large spin magnetic impurity can do to them. But even before I get to that, there'll be a long introduction since this is going to be the first talk about 2D topological insulators. So the work I'm going to present was done in collaboration with Igor Burmistro from Madhava Institute and his former twin students, Vlad and Pavel Korilovich, and the later part on law is also with Yuval. So let me mention before I start that in my group we have some other works recently related to edges of topological systems. I will not discuss them further, but I just mentioned them, and if anyone is interested, I will be glad to discuss them later on. So one of them has to do with Hall viscosity. It's an anti-symmetric time-reversal symmetry breaking term in the viscosity tensor that appears in a quantum Hall in any system that breaks time-reversal symmetry. And it's usually a bulk effect, but it can also have an effect on the dispersion of edge magnetoplasmons. And as opposed to bulk magnetoplasmons, where the effect is only second order in Q, here it affects already the velocity. So this might be a good way to find this Hall viscosity in an experiment. And in a quantum Hall system, it could have some topological meaning. So therefore, it could be interesting. Another recent work has to do with some boundary between two quantum Hall systems, 2/3 and 1, where in a bilayer setup there is a wide regime of parameters where you start from totally repulsive interactions, and at lower energies you get an effective model with effective attraction or superconducting correlations along the edge. And some other work, again, that I'm not going to discuss, which has to do with inducing topology and therefore also edge dynamics using driven and dissipative dynamics, so not going out of the equilibrium setup. So all those things I'm not going to discuss further, but let me go to two-dimensional topological insulators first in general, and then what magnetic impurities do to them and how that might be related to experiments. Okay, so what are two-dimensional topological insulators? So we heard a lot about quantum Hall systems, and one way to describe a quantum Hall system is to say that we start from a one-dimensional spinless fermions, where we have right and left movers, and we separate the right and left movers on the two edges of a two-dimensional gapped system. And this can only happen if the gapped bulk in between is special, has some topological properties. So it needs to be a quantum Hall with some topological number. And if we manage to do that, then this is nice, because when we have a chiral edge mode, then even if there is some scatterer, it cannot backscatter us. There is nowhere to. So we expect to have a perfect conductance of E²/H. This is the filling one quantum Hall effect, and we saw a lot of that. So in the same way, if we start from a spinful time-reversal symmetric one-dimensional system, we have right and left movers with spin up and spin down. And then we can imagine that maybe we could split them such that we'll have a two-dimensional gapped system, which is topological non-trivial. On one side, we will have right movers with spin up and left movers with spin down. And on the other side, we'll have the other thing. So this we will call helical edge modes. And if we manage to do that, this could be nice. Although on each edge there are right and left movers, and in principle you could backscatter, but because of time reversal symmetry, as long as you do not apply a magnetic field and there is no spontaneous breaking of time reversal symmetry, then at low energies you expect that you can only have elastic scattering, and no elastic or single particle backscattering is actually allowed because of time reversal symmetry. So you expect you will get a quantized conductance of E²/H per edge without applying a magnetic field. Now, of course, to create this strong coupling of spin direction and direction of motion, you need a strong spin orbit. And those works suggested concrete systems where this could be expected. So one of them, this was also the first to be discovered in experiment, is mercury telluride. It has a similar band structure to cadmium telluride, but with those two bands flipped because of spin orbit, and this band inversion actually makes this system topologically non-trivial. So if you build a quantum well where mercury telluride, there is a thin layer of that between cadmium telluride, then if it is too thin, it inherits the band structure of cadmium telluride, and then it is topologically trivial. But if it is thick enough, then we have the band inversion due to spin orbit, and this is topologically non-trivial. And then came a later suggestion that if we have a quantum well made of both indium arsenide and gallium antimonide in some host, then we have an electron band, sub-band here, and a whole sub-band here, and they couple, and this coupling also creates some gapped region, which is topological non-trivial and should carry edge modes of the type I described before. And then later on came suggestions about other two-dimensional materials like bilayers of bismuth and now very popular transition metal decalcogenides. So then experiments come, and the first experiments are already more than 10 years old. So what they see is the following. They measure resistance in mercury telluride as function of gate voltage. They find that when the gate voltage is such that the Fermi energy is either in the conduction band or in the valence band, and this is a usual conductor, and then the resistance is low. When it is in the gap and the system is topologically trivial, then the resistance is high. When it is in the gap and the system is in the topological regime, then we get something which looks like quantized conductance of 2 squared over h or e squared over h per edge. And a few years later, similar things were observed in the other semiconductor system. More recently, people have seen things in bismuth bilayers. Those are harder to interpret because they cannot make a separate bilayer. It's a bilayer on top of bulk of bismuth, and they use some STM to probe it. So the results are not as nice, but they seem to be in the right direction. And even more recently, there are those transition metal decalcogenides, some family members of graphene, but with more complicated elements with strong spin orbit, and some of them are expected and seem to also show this quantized conductance coming from being topological insulators. Now, even here, the samples are very they are very short, only a few tens of nanometers. So most of the real transport experiments are not done not here and not here. So in most of the following, I'm going to discuss the semiconductor systems on which there are more experiments. Now, not only we see quantized conductance, we know that it's coming from the edge. First of all, because if you make the system wider or narrower, the conductance almost doesn't change. Secondly, you can make a multi-contact probe, and you can inject current here, collect it from here, measure voltage between here and here, and then you get different quantized value, and you can calculate everything using Landau-Bittiker theory, assuming that you have just those helical edge modes going around and nothing in the bulk. And finally, people made Josephson junctions out of those, like the things we heard about in graphene, so they made it also in those materials. And from the effect of a magnetic field, you get some Fraunhofer pattern as function of magnetic field. And from that, you can extract the current distribution, and you also find that the current flows along the edges. And there are even experiments which use local probes, local scanning suite, that basically senses the local magnetic field. And again, you can convert that to current, and you find that in non-topological systems, current flows everywhere, but in topological ones, it basically flows only along the edge. So everything seems very nice, but people still are actually unhappy. And why they are unhappy? Because if we look closer, then in short samples of the order of a micron, we still see deviations from e squared to e squared over h, which actually are not eliminated even at very low temperatures, even in a dilution fridge. And what is even worse is that if you go to long samples, if you say 10 micrometer or more, you typically see resistive behavior, so resistance that is not quantized, but actually grows linearly with the size of the system. So this looks nothing like a quantum Hall, and it has pretty weak temperature and also gate dependence. This experiment, this is pretty old, and people think that this is due to heating, but better experiments came, and the results are not substantially changed. So the thing we get from that is that somehow there is significant backscattering on the edge, even at very low temperatures. And what can cause that? So this is an important slide, so let me go through that slowly and explain what is possible and what is not possible. Okay, so we understand that something is going along the edge. We have the edge modes, and there is some backscattering, so let's assume that there is some impurity, and it tries to backscatter right movers into left movers on the edge. And the right movers and left movers, I will not indicate them, but they have opposite spin wave functions, but I will just denote them by right and left. So a simple impurity will try to make a right mover into a left mover at x, not the position of the impurity, but this is forbidden by time reversal symmetry, so this cannot help us. So okay, the next thing is that maybe something inelastic is happening. So maybe at the impurity can help us change the momentum, and also there is some inelastic process, and this could be allowed by time reversal symmetry. Let me skip this comment for a minute. And then let's assume that the edge is non-interacting, but there are some local interactions near the impurity. So then what would you expect? So you could have a process where you take two right movers into two left movers. This is allowed by time reversal symmetry. The problem is that this is an inelastic process. Usually inelastic processes at low temperatures have a probability going as t to the power 2. And here, actually, because of the Pauli principle, we need to add those extra two derivatives. Each one of them gives us a factor of energy to the amplitude, or t squared to the probability. Overall, we have t to the power 6 divided by the energy of the gap, which is 10 millielectron volt. So at dilution-free temperatures, this should be very, very small, nothing like the deviations that we see in an experiment. Now, people can argue that I was assuming that it's a non-interacting edge, and the edge is probably interacting. It's probably described by a Latinger liquid. But the thing is that it is indeed a Latinger liquid. If you try to estimate the Latinger liquid parameter, basically it cannot be too different than what people observed in quantum wires in gallium arsenide, because it's basically the same dielectric constant. And then the Latinger liquid parameter deviates from 1, which is non-interacting, but maybe it's 0.7, 0.6. So the power will be reduced from 6, but it will still remain pretty high power. Still it doesn't explain what happens at very low temperatures. So in all the following, I will forget about interactions along the wire. They modify some of the results, but not the main message of whatever is going to come. Now, people later realized that actually a process in which you take two right movers and make them into a right mover and a left mover, they are also allowed by time reversal symmetry. This saves you 2 powers, this derivative, or 2 powers of temperature. This is still not good enough. So another thing people were thinking about is that, okay, you need to backscatter and you need to flip the spin, so let's consider magnetic impurity. And this also doesn't help easily. And why is that? If you have the usual model of a magnetic impurity, you start from a single level Anderson model and you are in a Coulomb blockade valley, you have a spin, then you are going to get some spin exchange, which could be a bit anisotropic, but of this form. So you would have term which basically contain S plus S minus. You take a right mover, you backscatter it, flip the impurity spin, and okay, you obtain backscattering. So this seems nice. But after you flip the spin, you send in another right mover, it cannot backscatter because the spin is flipped. You have to wait until a left mover comes, is backscattered and resets the spin. So you can only scatter right to left, left to right, right to left, left to right. So actually in the DC limit, it can do nothing. Even if you go to finite temperature, there'll be zero correction to the conductance. And that was noticed by Tanaka, Furusaki, and Matveyev in a few years ago. If you consider many impurities with interactions between them, which could order, this could become more complicated, but let me concentrate on the physics of a single impurity. So you need something more complicated to do backscattering. Okay, so let me mention briefly, just to set the stage, something that I was working on in the past, a few years ago, which is a model of extended defects and what we found there. So this is a picture of the actual heterostructure in the experiment. It has many layers. What is important to us that we have the layer of the quantum well, and we have some doping layer somewhere away from it, and we have a gate. So this is a picture of that. And the point is that the doping is never uniform. And therefore, maybe I'll go, okay, let me go here. So if we have an undoped system, this is an undoped semiconductor. We have conduction band, valence band, the Fermi energy is inside here. Now, once we, in the actual experiment, it's always doped and then shifted by a gate to put the chemical potential in the gap. The problem is that because the doping is never uniform, then you are going to have regions of higher and lower doping, and therefore you are going to have fluctuations in the local gate, effectively, that is acting on the system. And if these are strong enough, and since the gaps here are typically 10 milli-electron volt, they are pretty small, so anything is strong enough, then you could have regions where the Fermi energy crosses the bands regions in space, and then you could have hole puddles or electron puddles. So your bulk is not complete insulator. It should have puddles of charge in it, and there are some experimental indications, I won't go into them, that those puddles, by some local probe, that those puddles do exist. So okay, so we have such a puddle, and this puddle could be next to the edge, and maybe it could backscatter. So let's think about it a little bit. If we have such a puddle, it's a small region into which electrons are confined, and then we have a helical edge coupled to the puddle. The puddle is basically like a quantum dot, and as we heard very nicely in the morning, in a quantum dot we have single levels with some energy separation, small delta, we have charging energy, and we have some coupling to the Fermi seed, to the helical edge, some tunneling rate gamma. So those are the scales of the system, and one can try to estimate all of them in this system, and they are basically, this is probably the hierarchy of scales if you try to estimate stuff. So then, okay, you have this puddle, and often people think, okay, there is this puddle, so it's a chunk of place where you are actually not gapped, so this could backscatter. But actually this is not true. As long as you maintain time versus symmetry, then if only elastic processes happen, the puddle will not help you. A right mover will enter, will do something, and go out as a right mover. You can show that explicitly, and it doesn't matter how complicated you can have disorder, spin orbit, it doesn't help you. You cannot backscatter, this is time versus symmetry. So you still need inelastic processes, just that you can have more interesting inelastic processes in a puddle. So, and here it depends on, okay, so the dominant interaction, because it's a quantum dot, is charging, but charging actually conserves the number of right of left movers, so charging by itself still does not do anything to you. So what you need to do is to consider corrections to the charging interaction, what is known in the jargon as non-universal corrections to the canonical quantum dot model. And those are small corrections in some small parameter, and they give you can give you the backscattering. What they can give you is that now it depends on where you are. If you are in a Coulomb blockade valley with an even occupation of the dot, then you have even number of electrons, so total spin is 0. And then what you could have is a right mover, two right movers entering, say, doing something inelastic in the puddle, and then becoming a right mover and a left mover and going back. So it's the same kind of processes, but now mediated by the puddle. It becomes better if you are in a Coulomb blockade valley with an odd number of electrons in the puddle. Then basically you have an unpaired electron in the puddle. It has a spin. It's like a magnetic impurity. But the point is that because it's a magnetic impurity more complicated than the usual model with many levels, so you can have processes where this enters. And then, okay, you backscatter and it goes back. So notice that you could have processes where a right mover became a left mover, and the spin of the impurity remained the same. So it's like an exchange term where you have Sz times Sx. And this kind of more anisotropic exchange is necessary in order to have backscattering, and you can have it if you have more than one level in the puddle, if you consider all the levels of the puddle. So you can write a model like that, you can calculate the coefficients, and you get basically this behavior, that if you go to very low temperatures, you always find the T⁴ that I mentioned, but now the relevant scale to compare that is not the gap anymore, which is much larger than that, but some other energy, which depends on where you are. If you are in an even Coulomb blockade valley, the number of electrons in the puddle is even, then the relevant scale is the level spacing in the puddle. If you are at the peak, the relevant spacing is the relevant energy is the rate gamma. And if you are in an odd Coulomb blockade regime, so you are going to have a net spin on the puddle, and because of the exchange between the puddle and the helical edge, you are going to have condophysics. So at 0 temperature, you are going to have a condo singlet between the puddle and the helical edge. So at 0 temperature, it's still not going to backscatter. It's only going to backscatter at low temperatures, but the backscattering is going to be significant all the way down to what is known as the condo temperature, the temperature below which this screening occurs, and this condo temperature can be exponentially small in the exchange, so exponentially small in the parameters. So this can give rise to significant backscattering even at pretty low temperatures. And then if you then think about, so basically then you say that if you have a short edge, then you have few puddles, and then you see maybe fluctuations as function of gate, because basically as you change the gate, you shift the levels in the puddle and you go between the different valleys. And if you have a long edge, then you have many puddles, and they basically sum up. Because it's inelastic backscattering, then they sum up incoherently. It's like adding resistances. And then you get this resistive behavior. And if you average properly, you see also that it has weak temperature dependence. I will not go into that here. So this is pretty nice. So basically, if I want to summarize what we concluded in those works, is that if you have those puddles, they can backscatter, but it always needs to be some inelastic processing happening. Elastic processes will not be enough. It's just that basically the electron that enters the puddle will stay there for a long time until it's emitted. So this is a long time or low energy. So backscattering can be significant until very low temperatures. At 0 temperatures, there's going to be no backscattering, but at very low temperatures, there could be backscattering. And it's most significant when we have an odd Coulomb blockade valley, where we have basically a magnetic impurity with weak anisotropy, which is sufficient to backscatter. But this motivated us to ask, with the puddles, we basically get effectively a magnetic impurity with weak anisotropy. Can we have a more significant backscattering? Can we have magnetic impurities that do better than the puddles? So it turns out that yes, and for that we started to think about large spin impurities. First of all, because they are there. So a natural dopant of cadmium telluride or mercury telluride is manganese, which is a magnetic atom with spin 5/2. So those things do happen in those systems. And secondly, is that if you try to write down the Hamiltonian for the impurity, you see that it gets interesting. You find two terms in the Hamiltonian. So one term is the exchange between the impurity spin, this is capital S, and the spin density of the environment near the impurity, this is the small s. And one thing you find generically, this was found by Bernd and collaborators a couple of years back, and also by my collaborators, is that if you start from a model of the exchange of that with the bulk, which is generally isotropic, and then do projection to the edge, but you start considering the entire bulk exchange, then project to the edge, the anisotropy of the geometry will naturally give you anisotropy in the exchange, and you will get all the terms that you need to backscatter, and anisotropy is of order 1, or meaning the terms like SZ, SX, which can backscatter, could be of the same order as the usual terms like SX, or SZ, SZ, and this is the order of magnitude. And another thing, which was not much discussed in all the works before us, is that once you have a spin which is larger than 1/2, then you can also have this kind of local anisotropy, or you can describe it as a first self-exchange. This is a local term coupling the impurity to itself. For spin 1/2, this is trivial, doesn't do anything. It's just unit matrix. But for spin larger than 1/2, it could have an effect. And again, this G could be some general matrix. And because this is a local term, not directly related to the edge, then it's very relevant under our G. It's going to dominate the low energy physics, so it's important to consider it. Its size could also be non-negligible. And another thing that you realize is that you can always choose axis in the spin basis. You can rotate the spin, the impurity spin, such that D will be diagonal. Then you'll make J more complicated, but we are in any case considering a general J. So you can make D diagonal. And furthermore, a D which is proportional to the unit matrix will come multiplied by S squared. This doesn't do anything. So you can also always subtract something times unit matrix and write it down as DZZ times SZ squared plus dxx times s squared, and without loss of generality, let me take dZz to be the larger element in absolute value, and to simplify the analysis, I will take it to be much larger, but the results do not change considerably if those are of the same order of magnitude. So let's see why this is important. Okay, so let's understand what's the low energy fate of this impurity. So somehow we discovered that although people considered Kondo models with some high spin, they usually considered models with all kinds of symmetries, and the generic anisotropy case was not considered, so let me tell you what happens there. So if dZz is larger than 0 and the spin is integer, this is the simplest case. So this is the energy of the impurity. It's basically dZz times Sz squared, so this is a parabola. And at low energies, below the scale of dZz, we prefer to sit here at 0 as Z. So basically, the local anisotropy quenches the spin. And then at energies below dZz, the only things that you can do, you are here, but you can make virtual processes in which you go here and go back and backscatter something. So you can have backscattering, which goes as T to the fourth or voltage to the fourth, the usual stuff. You scatter two right movers into a right mover and a left mover, and the coefficient is going to be something proportional to the square root of J squared over dZz because of this virtual process. So in this case, you get pretty weak backscattering. This does not help you so much. If dZz is still larger than 0 and S is half integer, it's a bit more interesting. Then this is the energy level diagram. Those are your lowest energy levels of the impurity. So you have two of them, Sz plus or minus 1/2. So effectively at low energies you are here. It behaves like a spin 1/2 just with modified exchange because of the different matrix elements. And then we know that it will be Kondo screened by the edge, so there will be a Kondo singlet. At 0 temperature, it's not going to backscatter. At temperature which is low with respect to Kondo, you're going to have this behavior, but Kondo temperature could be pretty low, and above it you could have backscattering. So this is slightly better, not much better. Things become better if we are in the case where dZz is smaller than 0. Then if S is integer, we have now the inverted parabola, and the lowest energy states are either Sz equals minus S or plus S. Okay, and now it looks like a spin 1/2, but now we need to consider the smaller term dxx. Dxx changes its Sx squared. It could change the spin, the Sz, by 2 units. So it can couple, for example, in this case, from here to here, if we have a virtual process through those states here. So we are going to have something which looks like a magnetic field on the spin 1/2. It's actually not a magnetic field. It doesn't break time reversal symmetry. There is no Kramer's theorem because S is integer. But we are going to have a term going like dxx over dZz to the power S, so quite small if S is large, which splits those two energy levels. So we are going to have backscattering and temperatures larger than that, and that could be pretty small. Temperatures lower than that, again, we are going to get the T to the fourth, but now we see that significant backscattering can survive to pretty low temperatures if S is large. And it becomes even better if we have the same sign of dZz, but S is half integer. In that case, again, we have those two states. And now if we try to use dxx, it cannot take us all the way from here to here. And this is not just a mere something of this Hamiltonian. This is guaranteed by Cramer's theorem. So if we took more complicated, higher order terms, they would not change the picture. So the best you could do is use dxx to go almost all the way and make this last step while doing some flipping of spin at the edge. So use the exchange to make the last step. So you're going to have an effective exchange between here and here, which is the original exchange times this factor, which is exponentially small in s. And therefore, there is going to be Kondo screening of this spin 1/2 due to the coupling to the edge, but it's going to be a Kondo temperature, which is exponentially small in J, which is exponentially small in S. So this could be very, very small. So in that case, indeed, at 0 temperature, there is no backscattering. At very, very low temperature, backscattering is weak, but this very low is indeed extremely low. And you could expect that in the experiment, you are always well above it, and then backscattering could be significant. Okay, so backscattering could be significant because in the experiment, we are effectively much higher than the Kondo or other screening temperature. So now we need to analyze that. So we went to do that. So in the first stage, we calculated the average current. And since we are above the Kondo or whatever relevant scale, so we can use a master equation, we need to be a bit more, we need to do it a bit more carefully than usual. So usually in quantum dot physics, there is a regime where you can use a master equation, but you forget, you assume that your density matrix is diagonal, you forget about coherences, and this is perfectly valid because you are talking about charging states. Here you need to remember about coherences because coherences is basically allowing the spin not to point just in the z direction, but in along some other axis. So we need to write a full-fledged Lindblad equation and solve it. It can be solved exactly in some limits. In some other limits, we can do some analysis or some numerics. Let me just show you the results. So if the temperature or voltage are local, then the local anisotropy term, it's slightly simpler. You still have several computer energy scales. You have the temperature, you have the voltage, and the voltage basically gives you an imbalance between right and left movers along the edge. So this is like a magnetic field, which through the exchange also affects your impurity spin. And also you have a relaxation rate, so you have many rates to compare once against the other. And therefore, if you look at this is the correction to the conductance, it's basically I over V as function of V. This is the nonlinear conductance. Then for S equals 1/2, it just grows monotonically with voltage. And for larger S, because you have all those scales, you can actually have some non-monotonic behavior. And then if you go to lower temperature and voltage, and you need to consider also the local anisotropy, then you have additional scales coming into the system, and then you have different regimes, and you could have a pretty complicated IV, which if one measures that in an experiment, so from that one can extract all the different parameters of the local impurity. So this could be an interesting way to prove very sensitively the magnetic structure of a magnetic impurity. If it is just in a usual system, you are not sensitive to that, but near a helical edge, you are sensitive exactly to that. Okay, so there are all kinds of details, and it's different between integer and half-integer spin. But those are details. Let me skip them in the interest of time and come to the last part, which has some interesting qualitative picture. And this is what happens when you look at the shot noise. So let me discuss now, in the last part of my talk, what is going to happen with shot noise in the system. Okay, so just first of all, definition. So shot noise is defined. We apply some voltage, and we are looking in the large voltage limit. And we have current fluctuations. So we look at the noise in the backscattering current. So the current is E squared over H times V minus backscattering current. We look at fluctuations in backscattering current at 0 frequency and divide them by 2E times the average backscattering current. And this is what is known as Fano factor. And usually we interpret Fano factor, and sometimes this is a legitimate interpretation, as the charge of the entities which are scattered or backscattered in the system. Okay, so first thing to consider is what happens at spin 1/2. So for the case of weak anisotropy, basically for puddles, this was considered by Varonen and Glasman recently, and we found that actually you can find a general solution for for general anisotropy for spin 1/2. And this is the picture. So let me explain what is appearing here. There are several formulas. So first of all, if we have spin 1/2, then we can forget about the local anisotropy. It's not relevant for spin 1/2. And then we have just the exchange, and we can rotate the axis of the impurity S. We do not rotate the edge S. This is not free for us, but the impurity S we can rotate and make J to be lower triangular, so to have this form. And then it turns out that there are two combinations of the 6 elements appearing here, which we call B and C, and everything depends on them. This is the result for the Fano factor, and this is a color map of the Fano factor as function of them. And one thing that you can notice from that is that the Fano factor is always between 1 and 2. And this seems very reasonable. Why? Because we have two terms that can backscatter. We have terms like that, which are SZ, SX. It means that you backscatter something on the edge and don't do anything to the impurity spin. So this causes single particle backscattering. This should give you Fano factor of 1. And then there are terms here. So if JXX is different than JYY, or JYX is not 0, then you have terms like S plus, where you backscatter something on the edge and flip the impurity in the wrong direction. So you flip on the edge from up to down, and also in the impurity you flip from up to down. So this acts like a 2-particle backscattering, and this should give you a Fano factor of 2. And then you say, okay, I have a little bit of this, a little bit of that, so the result should be between 1 of 2, and this is what one gets. Now, okay, you go on to spin larger than 1/2, and you say, okay, could it be different? I mean, this argument remains the same. You can say, okay, for spin larger than 1/2, I should add the local anisotropy. But I'm looking at large voltage, and when voltage is larger than anything else, this is when usually people define Fano factor, then I can actually neglect the local anisotropy. So it seems that I should get exactly the same answer as for spin 1/2. Okay, so we just wanted to check, so we calculated numerically. And this is the result for spin equals 1. And then we find that not only it deviates, it can become larger than 2, but actually here we had to cut the color map, because actually when this combination C goes to 0, the Fano factor actually diverges, so you can get a Fano factor which is as large as you want. So this indicates some kind of electron bunching. Is it some kind of superconductivity along the edge? It is not. So we felt a little bit better, and we have an explanation for that. So let me try to explain the main features, basically, that one sees in this diagram. And if you increase the spin, then the picture is more or less the same. This central region is just becoming wider. So this is qualitatively the general picture, and let me explain what is going on here. So the typical thing that you have is that the Fano factor is close to 1, and especially if your spin is large, it's going to infinity. Then what happens there is that if the spin is large, you can think about it as a classical spin. It doesn't move, it just stays there. And because you have terms like SX, SZ, SX, then it can just backscatter. It acts like a local magnetic field, which does single particle backscattering. So you get Fano factor close to 1 with corrections which are proportional to 1 over S. This you get in most of the phase diagram. Okay, now if you go to this region of this parameter B, this combination close to 1, then the Fano factor goes to 1 for any S. And the reason for that is the following. So if you analyze what the distribution of SZ of the spin looks like when you solve the master equation, you find that it assumes in the large voltage regime a Gibbs-like distribution, where the Gibbs parameter theta depends on this combination B, and when this B is close to 1, then this theta is basically going to infinity, the impurity is polarized. Basically, when B is going to 1, this part of the exchange is close to being just diagonal, just isotropic, and then the impurity wants to be, because you apply large voltage, so you polarize the edge, and the impurity wants to be aligned with that, so the impurity is polarized. When the impurity is polarized, it basically sits there, and it does backscattering because of those terms. So you get Fano factor of 1, and then you have small deviation. If you deviate from b equals 1, you have small corrections to that. On the other hand, okay, so this is less interesting. What is interesting is what is happening here. Here you can get a large Fano factor. How do you get that? So let's look at the spin equals 1, and this is the regime where this c is going to 0. Now, when c is much smaller than 1, if you look at it, so you need to have the denominator here much larger than the numerator, and for that you need jzx and jzy to be the dominant terms in the exchange. So those terms here need to be the dominant terms in order to make c small. So it means that this is the main thing that does backscattering. You don't do anything to the impurity, it just sits there and you backscatter on the edge, but the amplitude of backscattering depends on the SZ of the impurity. Now you have S equals 1. Suppose you start with SZ equals 1, then you backscatter, backscatter, backscatter. At some point, you will have a wave event coming from the other elements here, which flips the impurity spin. Now it's SZ equals 0. And now the amplitude is 0, you do not backscatter. And then you wait some time, it flips X again, you backscatter again. So you have backscattering of many electrons, then you rest, then you backscatter many others. So you have bunching of electrons. And this bunching can be arbitrarily large if you make C smaller and smaller. And this gives rise to this very large Fano factor. And finally, you can take it to the extreme if you also take this combination B to be small. In that case, basically, this is quite different from isotropic, and then the impurity is not aligned with the edge spin. There is some equipartition of SZ. Almost all values of SZ are equally probable. And in that case, you basically say that I go around between the different values of SZ, and there are S values of them, and I go between them like a random walk. So I go between them in time of S squared. So I have bunching of electrons. The electron backscattering is modulated on time scale, which is proportional to S squared. So I have Fano factor, which is 1 plus S squared over C. So we have the 1 over C divergence multiplied by a large factor S squared. So we can get a very large Fano factor. So basically, this is the end of the story. So except for the introduction and reminding you about some old works of ours, what was the main topic is the new work about large spin magnetic impurities. We have seen that they can give rise to strong backscattering, and maybe this is what is seen in the experiment. To examine that carefully, one needs to look at the IV very closely. And then our predictions are as follows, that although at 0 temperature, always some combination of the local anisotropy and the edge are going to basically screen the impurity. So at 0 temperature, you should have perfect conductance. The screening can occur at an anomalously low temperature, and it could well be that even dilution fridge temperatures are much larger than that. So the impurity is basically typically not screened, and then you could have a significant backscattering and a pretty rich structure in the IV. And in the shot noise, again, you have a rich structure, but you have one interesting qualitative feature. You can have Fano factor much larger than 2. You can have bunching of electrons induced by the scattering by this large spin impurity. Thank you for your attention.